Let's draw the Lewis structure of SO3, which is sulfur trioxide. To accurately depict the Lewis structure of SO3, follow these steps. Begin with a rough sketch. Illustrate the chemical bonds between the atoms. Identify and mark lone pairs on the atoms. Ensure all atoms have complete octets. Conclude by calculating formal charges, aiming for a stable Lewis structure with the least formal charges possible. Before sketching the rough diagram, let's begin by calculating the total number of valence electrons and then determine the central atom. The total valence electrons in SO3 can be calculated by summing the valence electrons of each atom. Both sulfur and oxygen, members of group 16, contribute 6 valence electrons. With 1 sulfur and 3 oxygen atoms in SO3, the total valence electrons calculation is 6 for sulfur plus 6 for oxygen multiplied by 3, resulting in a total of 6 plus 18 equals 24 valence electrons for SO3. When determining the central atom for SO3, position the element with the lower electronegativity at the center. With an electronegativity value of 2.58 for sulfur, which is lower than that of oxygen at 3.44, we choose sulfur due to its lower value. Therefore, for the preliminary sketch of SO3, position sulfur at the center and place 3 oxygen atoms on the outside. 2 electrons represent a single chemical bond. Therefore, position 2 electrons on the left side to indicate the chemical bond between sulfur and the left oxygen. Similarly, place another 2 electrons on the right side to represent another chemical bond between sulfur and the right oxygen. In the same manner, position 2 electrons on the top to show another chemical bond between sulfur and the top oxygen. This way, out of the 24 total valence electrons, 6 are utilized, leaving 18 electrons unutilized. Lone pairs consist of electron pairs not utilized in chemical bonding. Remember, each pair comprises 2 electrons. Since we have 18 electrons remaining, we can form 9 electron pairs from them and mark these pairs on the structure as lone pairs. It's important to note that sulfur, a period 3 element, can keep more than 8 electrons in its last shell, whereas oxygen, a period 2 element, cannot hold more than 8 electrons in its valence shell. One more thing to remember is to always start marking lone pairs first on the outside atoms and then on the central atom. In SO3, each of the 3 outer oxygen atoms receives 3 lone pairs, while the central sulfur atom does not receive any lone pairs, given that we only have 9 lone pairs to allocate to the structure. It is evident that the octet is complete on the 3 outer oxygen atoms, but not on the central sulfur atom. Thus, let's proceed to fulfill the octet for the central sulfur atom. Sulfur already possesses 6 valence electrons and requires 2 more to complete its octet. Therefore, we will convert 1 lone pair from a specific oxygen atom. In this case, we will use the top oxygen atom and transfer it to the sulfur atom to form a chemical bond. Now, it is evident that both the central sulfur atom and the 3 outside oxygen atoms all form an octet. Thus, the octet rule is satisfied, and we need to check the formal charge to determine the stability of the structure. This is the formula we can use to calculate formal charges for the SO3 Lewis structure. Formal charge equals valence electrons minus non-bonding electrons minus half times bonding electrons. Input the data and place the values to derive the formal charges for each individual atom. For sulfur atom, valence electrons are 6, non-bonding electrons are 0, and bonding electrons are 8. So, the formal charge will be equal to 6 minus 0 minus half times 8, which equals to plus 2. For top oxygen atom, valence electrons are 6, non-bonding electrons are 4, and bonding electrons are also 4. So the formal charge will be equal to 6 minus 4 minus half times 4, which equals to 0. For left and right oxygen atom, valence electrons are 6, non-bonding electrons are also 6, and bonding electrons are 2. So, the formal charge will be equal to 6 minus 6 minus half times 2, which equals to -1. The formal charges of both sulfur and oxygen atoms are mentioned, and it is clear that the current structure is not stable, as there are still formal charges on the atoms. To resolve this, we will proceed by modifying the distribution of lone pairs and recalculating the formal charges. Again, recall that sulfur is a period 3 element and can hold more than 8 electrons in its valence shell. Sulfur already possesses 8 valence electrons, and now will convert one lone pair from each left and right oxygen atom, transferring them to the sulfur atom to create a chemical bond. This adjustment is made so that the formal charges on atoms are closer to 0. Let's check it by recalculating the formal charges and also check if the current structure is more stable than the previous one or not. We will use the same formula again. Formal charge equals valence electrons minus non-bonding electrons minus half times bonding electrons. For sulfur atom, valence electrons are 6, non-bonding electrons are 0, and bonding electrons are 12. So the formal charge will be equal to 6 minus 0 minus half times 12, which equals to 0. For each oxygen atom, valence electrons are 6, non-bonding electrons are 4, and bonding electrons are also 4. So the formal charge will be equal to 6 minus 4 minus half times 4, which equals to again 0. The formal charges of both sulfur and oxygen atoms are mentioned, and it is now evident that the current structure is more stable than the previous one, as formal charges on each atom are 0. Therefore, this structure is the preferable stable Lewis structure of SO3. To represent a pair of bonding valence electrons, we can simply replace 2 dots with one horizontal line. Since there are 2 pairs of electrons between sulfur and each oxygen atom, draw 2 horizontal lines between sulfur and each oxygen atom, indicating that sulfur is double bonded with 3 oxygen atoms. All right, there you have it, the Lewis structure for SO3. If this breakdown was helpful, give it a thumbs up, share the video, and subscribe to the channel.